All right. All right. So 7.2, we are layering on the identities. Okay. So this is definitely one of the things that makes trig hard, is that if you only kind of get some of the stuff we've done and all of a sudden we're using that to learn even more stuff, that can feel very overwhelming. Okay. But the good news is, on the flip side, if you invest time in clarifying that sort of beginning part, then it's a little bit easier to layer on the different pieces, all right? So what do we know? Well, by now we should know how to verify trig identities using reciprocal identities, quotient identities, odd even, cofunction, Pythagorean, and a whole bunch of algebra. Okay. If that is not where you are now, I would highly encourage you to spend some time this weekend and next week getting really comfortable with that. Okay. That's going to be a large percentage of exam 3. And exam 3 is happening in just about 2 weeks. Okay. So what's new? Well, we're learning more identities. There are more identities, and this is just the beginning, okay? There are more identities. We're gonna learn how to use them to find some trig values, but then we're also gonna learn how to use them to verify trig identities, okay? So now we're not just saying, hey, these are some tools that we can use, but we're gonna be adding on to those tools, all right? All right, so without further ado, let's get started. So the first thing we're going to talk about is the sum and difference formulas or identities for sine, okay? So these formulas can be used to calculate the signs of sum and differences of angles, all right? And so when we look at this, we've got two really similar looking formulas, all right? So it's really important that we figure out how they're similar and how they're different. But when you have sine of alpha plus beta, okay, so alpha is just an angle, and beta is another angle, okay? So we've got alpha is an angle and beta is an angle. And so if you have two angles that you want to find the sine of, like when you add them together, you don't just do this, okay? So you don't just take sine of alpha plus beta. That's not going to be equal to sine alpha plus sine beta. Okay, so what we cannot do here is we cannot distribute the sine. Cannot distribute Is that enough warning there? You cannot distribute the sine. Okay, do not distribute the sine. Do not do that. 100%. If I see someone do this on exam 3 or the final, I'm going to be super, super upset about that. Okay. If you see a sine of two angles out there, yeah, if you see a sine and you're looking to add two angles, instead what you need to do is plug it into this formula, okay? So sine alpha times cosine beta plus cosine alpha times sine beta, okay? So that would be the sum formula for sine. Now, if you have a difference of two angles, so let's say you wanted to do like two angles and you're subtracting them instead of adding them, what's the one thing that changes between the formulas? Yeah, exactly. One is subtracting and the other one is adding, okay? And so sometimes, instead of writing them as two separate formulas, especially if you're trying to like save room on a reference sheet or something like that, sometimes we take these two formulas and we write them together as one. And we just make sure we know that like if we're adding, that we have to add on the other side. And if we're subtracting, we have to subtract on the other side, okay? And so sometimes we write it as a single formula like this. we'll say sine of alpha plus or minus beta. Okay. So that plus and minus is kind of like the, what's it called? In the quadratic formula where you have a plus or minus and you kind of end up with two answers because you have to do one with plus, you have to do one with minus. We're using that same symbol here to talk about the plus and minus that we have to choose from here, okay? Now, the right-hand side is going to be sine alpha cosine beta plus or minus cosine alpha sine beta, okay? Now, if I were reading this formula, all right, let's just be really careful about what this means. It means that if I want to use the plus on the left-hand side, I use the plus on the right-hand side. Does that make sense? Because it came from this plus and this plus. However, if I wanted to read the minus sign on the left-hand side, I would need to use the minus sign on the right-hand side. Okay, so minus and minus. All right, any questions about that part? How we have the plus plus and the minus minus? All right. So let's take a look at how we use these equations, okay? So we've got two examples here, all right? One is in degrees and one is in radians. And so when you think about it, as you're sort of studying and making sure that you practice, you wanna make sure you practice both versions. You wanna practice some with degrees, but also some with radians, okay? So if we take a look at example number 1, I see that I'm gonna use the subtraction one, right? I'm looking at sine of 45 minus 30. And so we can say here that alpha equals 45 degrees and beta equals 30 degrees, okay? Does that make sense how I found the alpha and the beta from the equation? Yes, okay. And so all we're gonna do then is we're gonna pick the equation that has the minus, and we're gonna go ahead and plug in 45 everywhere we see an alpha and 30 everywhere we see a beta. So that's gonna give us sine of 45 cosine of 30 minus cosine of 45 sine of 30. Okay, so all we've done is just plug in the numbers into our equation. Now from here, we're gonna go ahead and plug in the values from our unit circle, all right? So you go to your unit circle, you find 45 degrees. The sine of 45 degrees is root 2 over 2. And then you're going to go to 30 degrees, and you're going to find the cosine of 30 degrees, and that's going to be root 3 over 2. Okay, so instead of writing sine of 45 times cosine of 30, I just found the values from my unit circle. What am I going to write then for cosine of 45 and for sine of 30? Root 2 over 2, good. And for the sine of 30, and a 1/2, beautiful. All right. So now we're done using our formula. Now we're just gonna clean this up a little bit. So when we have root 2 times root 3, we actually get root 6. And when we have 2 times 2 on the bottom, we actually get 4. Okay, so that first set of fractions goes to root 6 over 4. What does the second set of fractions go to? Good, root 2 over 4. Okay. Well, we kind of talked about this earlier when we have two fractions and we want to combine them with a subtraction or addition, we have to have the same denominator. So this is pretty nice because it gives us the same denominator, right? And so then what we can write is root 6 minus root 2 over 4. Okay. Now I do want to point out another really common mistake here, which is if you're here and you keep simplifying and you do this. First of all, this is in red, so you better not do this. But if you did, okay. The thing that makes this wrong is that these two are not equal to each other, okay? When we have square roots, we can't just like, if we have an addition or a subtraction, we can't just break those apart and then do them separately, okay? So we cannot simplify our answer any more than what we have here, all right? So don't get too excited. Don't keep going and trying to find like an even more simple answer. All right. Let's take a look at example 2 here. All right, so same kind of process, but we're doing this with radians because again, as we sort of move forward in math, the more we work with radians, hopefully, the more familiar we get with them and the less afraid we are of them, okay? All right, so if we look at example 2, we've got alpha equals 3 pi over 4, and we've got beta equals 2 pi over 3. And so when I plug things into the formula, I'm going to need sine of 3 pi over 4 times cosine of 2 pi over 3. And then is it going to be plus or minus here? It's going to be a plus. Good. So plus cosine of 3 pi over 4 times sine of 2 pi over 3. All right, so all of that is just plugging things into the formula. And now, just like we did with degrees, we're going to go ahead and pull all of the values from the unit circle, okay? So for sine of 3 pi over 4, we've got root 2 over 2. Cosine of 2 pi over 3 is going to be a negative 1/2 plus, let's see, that one gives us negative root 2 over 2 times root 3 over 2. Okay. And so that's why we kind of spent a lot of time in the beginning of this 8-week course talking about finding values on the unit circle, because we want it to be quick like this. We don't want to be hunting too long for the particular angle or thinking like, is sine the x or the y value? We want that to really come as second nature for us so that we can answer more complicated questions, okay? All right, we're going to clean this up the same way we did before. The first fraction is going to give us negative root 2 over 4. The second fraction will give us negative root 6 over 4. And we can combine those to make negative root 2 minus root 6 over 4. Okay. So example 1 and 2, really just kind of showing you how to use that formula right there, right? Once you have your alpha, once you have your beta. But one thing we want to be really good at doing is not just saying, oh, they gave us alpha, they gave us beta, and so then we just go ahead and plug into the formula. Like, honestly, that's kind of boring. So where we're going is more questions like example 3, okay? Where we want to think instead, how do we come up with 11 pi over 12 from two nice angles on the unit circle, okay? And Thea, I think that you'll find most of the time that a common denominator kind of happens. It's not that you need it, but the way these numbers work out, typically you'll have a common denominator, okay? All right, so the game we want to play with ourselves for example 3 is this. We look at our angle and we ask ourselves, how do we use two unit circle angles to make 11 pi over 12? Okay. All right, so since this is the first one that we've seen, let's kind of think through this one together, okay? But this is a good place to kind of study a little bit, is like, how do we make these nice or these not so nice angles from some nice angles, okay? Now, the way that I typically think about it is I write out for myself two fractions that have the same denominator that I have in the question. So I have a denominator of 12, so I'm going to write it with a denominator of 12. And I also know that it's like something pi over 12, right? Because we're looking at radians here. And so the question then is less about fractions and adding fractions, but really, I want you to find two numerators from the unit circle that add or to make 11. So like, how do we add, what two numbers can we add? And they don't have to be on the unit circle yet, but what two numbers can I add to make 11? And I'm sure some of you would say like 10 and 1, right? We could do 1 plus 10 equals 11, right? Thea says 7 plus 4 equals 11. What else can we add to make 11? 5 and 6, 8 and 3, good. Okay, so 5 plus 6 equals 11, 8 plus 3 equals 11. Okay, I think maybe we can kind of stop there, right? So we've got some choices here. But what we want to do is think about, of these pairs, when we plug them in here, are we going to be able to reduce to get a nice angle from the unit circle? So for example, if I put in a 1 pi over 12 and then a 10 pi over 12, I know that 1 plus 10 makes 11, right? That everybody knows. 10 pi over 12, what does this reduce to if I wanted to reduce my fraction? Good, that reduces to 5 pi over 6. And is that on the unit circle? And I think we'd all be like, yes, it's on the unit circle, right? So that one seems good. 1 pi over 12, what does that reduce to? It stays the same, okay. Is 1 pi over 12 on the unit circle? Like, is it one of those quote unquote nice angles that we got from the unit circle? No, right? So 1 and 10, even though they add up to 11, I don't think that's the best choice for us because we aren't able to get back to unit circle value, okay? So I'm gonna leave these here just so we can kind of see, like, this one was okay, but this one kind of disappointed us. All right, let's try another pair. So we tried 1 and 10. Which other pair might we want to try to see what reduces to a nice unit circle angle versus ones that might not? All right, let's try 8 and 3. Okay, so if we have 8 pi over 3, 8 pi over 12, and 3 pi over 12, well, 8 plus 3 gives you 11. That's totally fine. Okay, and let's see how they reduce. 8 pi over 12 and 3 pi over 12. What do those reduce to? Yeah, exactly. This first one reduces to 3 pi over 4, and the other one reduces to pi over 4. And I hope that those are pretty familiar to us as like nice unit circle values, right? So these ones would both be okay. Now, it doesn't always turn out this way, but in this case, we could have actually picked another pair. We could have picked 5 pi over 12. Wait, does that one work? Nope, just kidding. That one doesn't work. Never mind. All right. So let me pause here for what isn't it 2 pi over 3? Yep, sure is. Good morning. 2 pi over 3. Did we reduce the other one right? I'm sure you did. Did I write it right? Folks, I was so stressed out last night. Okay. Uh, you guys are so kind. I am basically wrong with arithmetic most of the time, so I wouldn't second guess that. Yep, gotta love mornings. Okay, so let me just pause here for a moment so I can kind of recollect. But what we've done so far is think about like when we don't have alpha and beta, how do we find alpha and beta? Okay, so it was a little bit of trial and error. Okay, and if you feel like you're strong with fractions, and I think this process isn't so bad. But if you've always kind of had a love hate, mostly hate relationship with fractions, you can still get away with thinking about whole numbers and then reducing your fractions afterwards, okay? So we can, like, we tried 1 plus 10 and that didn't work out, but we tried another pair, 8 and 3, and it turns out that that pair did reduce once we reduced it correctly, okay? So here we have a pair that works as our alpha and our beta. Okay. Now, what this means is that we can say alpha equals 2 pi over 3 and beta equals pi over 4. All right. And then we just plug everything into the formula. That's it. Um, that's a great question, Richard. So when we're looking at addition, it does not matter. When we look at subtraction, it's going to matter. Okay, so when we're adding, totally fine, doesn't matter which one's which. When you're subtracting, it will matter. Okay. All right, let's plug this into our formula. Hopefully we didn't forget that formula already. But really, we have sine of 2 pi over 3 plus pi over 4 is equal to sine 2 pi over 3 cosine pi over 4 plus cosine 2 pi over 3 sine pi over 4. And then turn the crank. Go to your unit circle, find the values, plug them in, simplify, okay? Let's see, sine of 2 pi over 3 times cosine of pi over 2 plus negative 1/2 times root 2 over 2. And you'll notice that we get a lot of the same kinds of numbers over and over again, right? We've got our root 6 over 4 minus root 2 over 4, which we can combine into a single fraction and call it a day. Okay. As you folks come back to these notes and study for exam 3, or I don't know, try and wing exam 3, I would definitely come back to this example, okay? There's a lot of pieces to this. We got to figure out the fraction piece first so we can find our alpha and beta, and then we use our formula. All right, let's take a look at 2 more uses of the sine, sum, and difference formula, okay? So sometimes we get an expression that looks something like this. And we're using numbers right now, but we might typically see this with just a regular alpha and a beta, or an x and a y. And so what we want to think is, where did this formula come from? Like, what's a shorter way of saying this formula? Okay. And so the first thing I'm going to do is I'm going to go ahead and take the first term and rewrite it so I have sine of 82 times cosine of 61 degrees. Okay. So really I'm saying, like, if I have like 2 times 3, it's the same thing as 3 times 2. So when I multiply, the order does not matter. Minus, I could do the same thing with the second term and have cosine of 82 sine of 61. Okay? So all I've done is rewrite the terms, switching the order of the multiplied terms. Okay? Why would I do this? Why would I take the time to rewrite things just so they're in a different order? And the answer is not because I'm a math teacher and not just for fun. Okay. So we cannot factor out the sine. Okay. So this is something I kind of want to go back to a little bit. Sine of 61 is 100% not equal to sine times 61. Okay. And so that's something I really want us to think about here. When we think about sine 61, and we spent a long time in the beginning of like this class talking about what sine is. You even had a test question on it. That is actually the ratio of 2 sides, opposite over hypotenuse, right? So we need the angle to go with it. Otherwise, we have no idea what ratio we're looking for, okay? And so even though it looks like sine times 61 or sine times 82, we don't want to think about it like that, okay? So sine and whatever comes after it has to stay together. But yeah, we really want to think about matching that formula we saw earlier, right? We saw a formula that said sine alpha cosine beta minus cosine alpha sine beta. And what was a shorter way of saying that? Instead of writing all of that out, we could have written it how? Exactly. We could have written this as sine of alpha minus beta. So, Richard, this was actually a really great question you just asked. Does the order matter? And in this case, it does, because we have that subtraction, right? So we want to identify our alpha. Our alpha in this case is the 82 degrees. And our beta is 61 degrees. All right, so we're literally just matching the pieces to the equation. And so all this whole long thing, cosine 61 sine 82 minus sine 61 cosine 82, is just another way of writing sine of 21 degrees. Okay, cool. Yay, I'm glad you made that connection. Okay, so again, we're not typically going to look at this with numbers, but it does work with numbers. And so it's important that we see that it works with numbers, okay? Because most of the time, we're going to be working with cases kind of like example 5, where it's going to be like maybe one variable and a number, or maybe 2 variables. We don't know yet, okay? So we're going to see a lot of different cases. So I chose one that only had 1 variable and 1 number, so we could kind of go from there, okay? So this says, verify the identity sine of x plus pi over 2 equals cosine x, okay? And so what we want to think is, when we try and verify, we pick the side that's more complicated, which in this case I would say is sine of x plus pi over 2. And we want to make it look like cosine x, because if we were to graph both sides on Desmos, we would see that they're the same graph. Okay. So we run through our list of identities, right? So I'm going to scroll back up to the top real quick. These are all the identities we learned so far. Can we use the reciprocal identity? Can we use the quotient identity? Can we use odd or even? Can we use cofunction? Can we use Pythagorean? So it's kind of a checklist on purpose, okay? And when we look at all those identities, which you should 100% have written on your reference sheet for exam 3, when we look at all these identities, we're trying to see like which one matches with which. What can we substitute out, okay? And it turns out that none of those really fit very well. None of the ones that we've learned up until this point fit very well. Well, what does fit well is the formula we just learned, the sum for sine. And so if I were to kind of write out here, I would use the sum for sine formula. And I would make the left-hand side, I would apply that formula, okay? So we could think about this case, x is like our alpha and pi over 2 is like our beta. So when we expand out, we get sine x cosine pi over 2 plus cosine x sine of pi over 2 equals the other side that we didn't touch yet. Okay, so it's one more trick to add to our bag of tricks on how to substitute out in an identity. Okay. Now, we do have some numbers here, which actually works out pretty well for us, okay? So what is the cosine of pi over 2? Let's find our unit circle and find cosine of pi over 2. What does that give us? Good, sine x times 0, good. And then what is sine of pi over 2? It's 1, good. Okay, so if you can, we look for unit circle values, right? And then it turns out that we can simplify a little bit, because sine of x times 0 is going to go to 0. And so we just end up with cosine x equals cosine x. And there we have it. Okay. So it's not that it's necessarily hard, it's just that in the mix of so many identities, you have to be able to find the right one. Okay, you have to be able to find the right one. All right, this seems like a good stopping place. All right, so it is 10:38. Let's be back at 10:50. Okay, so let me just type that into the chat so we have that. So we're gonna be back at 10:50, okay? And when we come back, we will finish up 7.3, all right? All right, so before break, we talked about the sum and difference formulas for sine, and I'm sure you're all so excited to hear that there's also a sum and difference formula for cosine, and there's also gonna be one for tangent, yay! So here we are on the second set of sum and difference formulas, okay? So the sum and difference formulas that can be used to calculate the cosine of sum and difference angles are as follows, all right? So let's zoom in a little bit so we can see this a little bit better. Cosine of alpha plus beta is gonna be cosine alpha cosine beta minus sine alpha sine beta. And cosine alpha minus beta is going to be cosine alpha cosine beta plus sine alpha sine beta, okay? And so just like we did earlier with the sum formula for sine, we can condense both of these equations into a single one, okay? And when we condense them, we really need to be careful about the plus and minuses. So when we're looking for a cosine sum, we actually end up subtracting on the other side, okay? And when we're looking for the cosine difference, we're actually adding on the other side. And so earlier when we talked about the sum one, I'm sure people were like, why is she making such a big deal of this? The reason I made such a big deal of the single formula for sine is because it's going to be a little different for cosine, right? So when we write our cosine one as a single formula, we can still write cosine of alpha plus or minus beta. Okay, so that part still stays the same. We can put the plus and minus together in a single equation, okay? And like before, the formulas are actually exactly the same except for the pluses and minuses. So we can write cosine alpha cosine beta. I'm going to leave a space, sine alpha sine beta, okay? Now here's the important part. What do I write in between the cosine alpha cosine beta and the sine alpha sine beta? Perfect. It's exactly going to be a minus over a plus, okay? And it's going to be a minus over a plus because the cosine alpha plus beta has a minus in the equation. And the cosine alpha minus beta has a plus in the equation, okay? And I want to make that really clear because, you know, when you have a formula sheet that's not usually color coded for you, so we really be aware of those differences. And I also think that separately, we've seen this plus minus symbol a lot. As soon as we learned the quadratic formula, we learned about the plus minus, but there is also a minus plus symbol, which just means that your first choice would be the minus and your second choice would be the plus, okay? So even though we're used to seeing it as the plus minus, it could also be minus plus, all right? Okay, so let's start off similarly to the way we did for sine. We're gonna go ahead and just practice using the formulas for 6 and 7. Okay, so we're gonna practice using it with alpha plus beta. And then for 8, we're really gonna look to think, what fractions can I add to make 7 pi over 12? And then we'll finish off with here's some numbers to just make sure we know how to go both ways in the equation. And we'll finish off with the verify the identity. Like, how do we use this in a situation where we really don't have that many numbers, okay? So let's go ahead and get started with 6 and 7, right? So in 6, we've got our alpha is 45 and our beta is 30, okay? And so when I write out my formula for cosine, I have cosine 45 cosine 30 minus sine 45 sine 30. Okay, so all I did was just grab those formulas from above, the plus one specifically, so the one with the pink circles, and I use that formula on the other side. Then I pull all my numbers from the unit circle and simplify. Root 2 over 2 times root 3 over 2 minus root 2 over 2 times 1/2. And that will give us root 6 minus root 2 over 4. Okay? So pretty straightforward, other than having a lot of radicals in there and fractions, but the process is very straightforward. Expand out using the formula, find the values from your unit circle, simplify. Right? I'm going to give you a moment to do number 7. Right? So go ahead and start working on number 7. And then I'll give you a bit of a head start, and then I'll start to fill in what I have for number 7. All right, wherever you are in your work, take a look at this first line. Does that match what you have so far? That makes sense where I got all the expanded terms from? Okay. And then we just need to make sure we plug in the right values and that we keep in mind that some of them might be positive and some of them might be negative, okay? And so when we do that, we get those terms. Okay, so I just found those directly from the unit circle, and I should end up with okay. Someone want to double check my arithmetic? I can already tell you I think I made a mistake on my answer key, so all right. Are we agreeing with the negative root 6 minus root 2 over 4? Yes. All right, thank you, Michelle. Okay. Yay. We can all be accurate with our calculations. Okay, so those are sort of our straightforward, like just practice plugging things into the formula, okay? And so this one, example 8, has a little bit more room because again, we want to think about like what numbers or what angles from our unit circle can we use to make 7 pi over 12, okay? And so I'm going to kind of start the same way. I'm going to set up one fraction plus or minus another fraction to try and get pairs that add or maybe subtract to make 7 pi over 12, okay? So I'll give you a moment to think about that. What might some numerator pairs be that will add to make 7? Okay, let's focus just on adding to make 7. Don't get too bogged down by like the fraction that it's part of or the pi. Okay, yeah. So we got like 1 and 6, 2 and 5, 3 and 4. Okay. And like if I put in 1 and 6, I think I can already see that that 1 over 12 is not going to reduce to a nice unit circle value. So let's try the numbers that Michelle suggested, 3 and 4. Okay. Well, we also want to make sure, we know 3 plus 4 makes 7, but we also want to make sure these fractions reduce to nice unit circle values. So we've got pi over 4. Well, that's good. That's on our unit circle. And we've got pi over 3, and that's good because that's on our unit circle. Okay? And so in this case, we don't actually need the minus sign because we found that 3 pi over 4 plus 3 pi over 12 plus 4 pi over 12 makes 7 pi over 12. Okay? And so what we really have is what is cosine of pi over 4 plus pi over 3. Okay? And we do not want to do this. Write it in red to make sure we don't do this. We do not want to do this. Please don't do this. Okay? You could make other mistakes on a test or a quiz, but please don't make this one. All right? Instead, we identify our alpha and our beta. And because this is addition, the order doesn't matter. I could have had alpha as pi over 3 and beta as pi over 4, okay? And we plug them into the equation. And we turn the crank. And we go to our handy dandy unit circle. We grab some values from there. And we simplify. We should end up with something like that. All right. Any questions on example 8? All right. Well, let's go ahead and, oh, perfect. Let's take a look at example 9 and 10. Okay, so I'm going to give you a few moments to kind of write out what you think you might be seeing here for number 9, like how do we match that one to the formula? And then for number 10, how can we use the new formulas we learned to expand or make those two sides equal to each other? Okay, so take a few moments and kind of start working on 9 and 10. And I'll start to put my work up there as well so we can see how everyone is doing. Make sure I didn't make any more mistakes. All right. If anybody has an answer for 9, go ahead and type that into the chat. All right, I think 10's a little harder to type in. Um, but let's at least get started with number 9, all right? Let's see what ideas we have on how that might match one of the formulas that we already have. Okay, what are you confused about for number? Is it for number 9? Yeah. Okay. Well, which formula does that look like from the cosine ones that we just learned, right? We just learned 2 new cosine formulas. So there's the cosine sum and the cosine difference. Okay. What makes you say the difference? Because there's a minus sign in between it? Wait, what? Yeah, okay. It's the sum formula, right? Okay. So maybe it would be helpful if we wrote those formulas out here. We know for the cosine alpha plus beta, we have cosine alpha cosine beta minus sine alpha sine beta. Whoa, beta. And we have this one. Okay. Ah, okay. So the question is, these numbers that they give us, which one, like, forget the numbers. The numbers are actually not important, okay? And I would not change it to radians because that's extra work that you don't need to do. We're looking here for the pattern of the sines and cosine. So I have cosine, cosine, sine, cosine. Ah, that's supposed to be a sine. So sorry. Okay. So you have cosine, cosine, sine, sine. Which one does that match with? Oh my goodness. Sorry, I'm so off my game right now. Okay. So if we have the cosine, cosine, sine, sine, that matches cosine, cosine, sine, sine. And which one is it? Well, it has the minus sign in there, okay? It's the worst when it happens in these moments too, because it's like supposed to be this big, like understanding moment, but then I just typed it wrong. That's like the worst. Okay, so now that we've cleared up Judy's giant mistake, hopefully we all can see now we're looking at this cosine sum. And so really this is saying find cosine of 225 plus 30 degrees, which will give us cosine of 255. Okay. Oh my gosh. Okay, so many mistakes. This is a plus. How does that change that? Well, that's going to make that a minus, and that should be 195. Is that better? I don't think the rain is gone yet. I think the rain is still right here. No, you're totally fine. I'm clearly the one who has not been proofreading my work here. You're totally fine. Okay. Should we do one more? Because that one was so bad. Okay. Example 9a. Okay. So let's say we had cosine of, I don't know, 100 cosine of 25 minus sine of 100 sine of 25. Okay. No typos this time. Promise. Okay. So now with 9a, that is typo free. Which identity does that look like? And how can we write this as a single cosine expression? That is the sum. Excellent. All right, that is the sum. Mhm. So we know it's a sum because the cosine one is kind of like backwards. Like when we have a subtraction in between there, it actually shows a sum. So if we want a sum, oh, it looks like my typos are catching on. Cosine of 100 plus 25 means that cosine of 125 is equivalent to this. Okay. That's not one thing I want you folks to learn from me, okay? That is definitely, definitely not. All right, does that clarify this one a little bit more? Okay,
Professor, I have a question.
for sure. What's up?
Um, I was, I don't know if this is gonna make sense. I feel like this is gonna be one of those things that sounds better in your head, but can we think about like when we use, like for example, 9 and 9a, we're kind of like, I don't want to say contracting, but like kind of contracting it together. And then for stuff like example 6, we're expanding.
Yeah, exactly.
Okay, cool.
Exactly. So if we think about like our condensing logs and expanding logs, it's kind of similar to that. Yeah, I don't know. I think some planets are in retrograde or something. Something's happening. It's weird. Okay, now let's take a look at example 10. So verify this identity, right? Um, so we can use all of these for like actual angles, but we can also use them to prove that like something cosine of x minus 5 pi over 2 is actually equal to just a regular old sine x, okay? And so if we think about our list of identities that we looked at earlier, it's already sine and cosine. So there's nothing I really need to change about that. But if we think about all the other identities that we know the quotient one, we know the cofunction, we know uh, the reciprocal ones, we know the Pythagorean ones. This one doesn't really match any of the ones that we learned previous to today, but it does match our difference of cosine. Okay, so we're going to use the difference for cosine. So cosine difference to expand out cosine of x minus 5 pi over 2. And so when we use that formula to expand, we'll get cosine x cosine 5 pi over 2 plus sine x sine 5 pi over 2. And we want to somehow show that that's equal to sine. Okay. All right. Now this again kind of goes back to that first week of class where I was like, oh, I want you to practice finding units or angles that are not on the unit circle. Like 5 pi over 2 is not one of the nice angles we see on the unit circle. So what angle is equivalent to 5 pi over 2? Yeah, it's the same thing as saying look for the angle pi over 2. Okay? So this is just looking for your reference angle. Okay? Now these kinds of things are important to show because some of you be getting some magical answers on exams where you're like, cosine of 5 pi over 2, oh, I totally know what that is, but you're not showing me the steps, okay? So make sure you show me, at least tell me like, this is the same as pi over 2, I know that, and here's where the number comes from, okay? And now when we substitute things in, we'll get cosine x times 0 plus sine x times 1. And this is very similar to the other one we saw, and we're going to end up with sine x equals sine x. Okay? All right. Any questions on all right. Well, folks, if there are no questions on 10, we're going to head off into the last of the sum and difference formulas, okay? So we don't learn them for cosecant and secant and cotangent. We just learn them for the three main trig functions, sine and cosine and tangent, okay? So your textbook gives these two as formulas for the sum and difference of tangent, okay? So tangent of alpha plus beta equals tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. And then the second one, the signs are all different, okay? And so we can take a look at these two equations and write them as a single equation using that plus minus or the minus plus, just like we did the other one, okay? What we can say is that tangent of alpha plus beta plus or minus beta equals tangent alpha. Leave a space. 1, leave a space. Okay. Now, let's go through the plus version first, okay? So when I get to between the tangent alpha and the tangent beta on the top, should I write plus minus or minus plus? Plus minus, good, because the plus one has a plus. So we want to have plus on the top. Okay. In the denominator, I have 1 space, tangent alpha, tangent beta. Exactly, and we're going to flip-flop those, minus, plus, because the minus is the one from the tangent alpha plus beta equation. Okay. And then over here, let's just double check we did it right. We've got minus, minus, and plus, and that's good because we have minus, minus, and plus. Okay. Now, if you don't want to write it as a single equation, you don't have to, okay? But one of the things about, as we sort of go higher in math is that it is helpful to understand how things are written, even if you choose not to write it that way. To be able to read it and interpret it is important, okay? So if you write 2 separate formulas on your reference sheet, that's fine with me. I just want you to, I want to make sure you know how to read it otherwise in case someone ever shows it to you as a single equation, okay? Now, these, you can tell we already have so many equations, right? We've got our sine equation, our cosine equation. We've got 2 of them for each of them. We have all the other identities we already learned. And so sometimes when it comes to tangent, I actually use sine and cosine to define my tangent, so it's not extra memorizing, okay? And so I'll show you what I mean by that. Go back to your notes, and what is the quotient identity for tangent? What is the quotient identity? Yeah, sine theta over cosine theta, okay? So now that's always true. Tangent of theta equals sine theta over cosine theta. So I'm going to use that to help me figure out tangent of alpha plus beta, okay? So what I mean by that is tangent of alpha plus beta is going to equal sine of alpha plus beta over cosine of alpha plus beta. Does that make sense? Like I'm using the reciprocal, I'm using the quotient identity, but I'm expanding it so that instead of having to memorize another formula for tangent, I'm going to cheat and use the formulas I already know for sine and cosine. Okay. This version that we're going to write down right now is sometimes more useful, okay? Especially if you feel like you have a hard time finding tangent on the unit circle. You can almost cheat your way there without actually having to use tangent from the unit circle. You can get away with only using sine and cosine from the unit circle, okay? So let's kind of show you what those formulas might look like. So if I have tangent of alpha plus beta, I'm going to go back into the notes, and I'm going to grab the sine of alpha plus beta formula, which is sine alpha cosine beta plus cosine alpha sine beta. Okay, so I just got that from like the first set of formulas we learned. And then I'm going to go back to the second set of formulas we learned about cosine of alpha plus beta, and I'm going to write that expanded form here. Right? So all I've done is go back into my notes and find a substitution for it. This is a perfectly valid formula to use for tangent of alpha plus beta. Okay, and we'll show in the next few problems how to use both versions so that we can kind of see which one we might like better as individuals. Okay, now we can do the same thing for tangent of alpha minus beta. So if we're going to find the difference, well, then I take the sine formula, but the difference one, so with a minus in there, and I'm going to take the cosine difference. And this would be another way that I could find tangent of alpha minus beta instead of using this form. Okay? So just to be clear, this formula and this formula, the ones with the pink dots, will get you the same information. And this one with the blue dot and this one with the blue dot will also give you the same information, okay? I'm not particularly picky about which one you use. You can use both of them. And like I said, we're gonna walk through both of them so you can kind of see which one you might like better, okay? All right. Is there anyone who still needs to write these down or are we good to move on? We good? We not good? Yes, Richard, we could combine those as well. I wasn't sure how people were feeling about the plus minus, so I didn't write it that way, but you can certainly do that. All right, cool. Okay, let's take a look at example 11. Okay, so for example 11, all right, so we're gonna practice. We know that this version already gives us the alpha and the beta, right? We know from here that alpha equals 2 pi over 3 and beta equals pi over 4, okay? And what we're going to do is show both versions of the formula. We'll do the one that the textbook gives us first, and then we'll do the one that I sort of wrote in the other box, okay? So if we use the one from the textbook, then we should see that tangent of 2 pi over 3 plus pi over 4 is equal to tangent of 2 pi over 3 plus tangent of pi over 4 over 1 minus tangent 2 pi over 3 tangent pi over 4. Okay, so that's just plugging it into the first equation. And now we have to be able to find tangent from our unit circle, okay? So what is tangent of 2 pi over 3? Negative root 3. Yeah. So we should get a negative root 3 for that. Okay. And tangent of pi over 4, well, that's just 1, right? So tangent of 2 pi over 3 gives me negative root 3. Tangent of pi over 4 gives me 1. Now, when I fill that in on the bottom, I get 1 minus negative root 3 times 1. And so I end up with negative root 3 plus 1 over 1 plus root 3. Okay? So this formula, not so bad. The trick here is you have to know how to find tangent. right? If you don't know how to find tangent without a calculator, you're kind of out of luck here. So let's say you're like, I really don't feel good about finding tangent on the unit circle. Well, we've got another formula for you to try, okay? So let's try that other formula. Now our answers are not going to look exactly the same, but if we type them into the calculator, they will be equivalent in terms of decimals, okay? So we're going to take sine of 2 pi over 3 cosine pi over 4 plus cosine of 2 pi over 3 sine pi over 4 over cosine 2 pi over 3 cosine pi over 4 minus sine 2 pi over 3 sine pi over 4. Okay. So yes, I think on first glance, this formula probably looks much more intimidating than the other one. But when we look to fill in values, we can just fill in values straight from our unit circle. We don't have to divide fractions on our unit circle to get here, okay? So I'll let you kind of evaluate that on your own in terms of a cost-benefit analysis, but we really want to think about what's going to get you individually to the right answer, okay? And so if we plug all of these values in, we'll get root 3 over 2 times root 2 over 2 plus negative 1/2 times root 2 over 2 over negative 1/2 times root 2 over 2 minus root 3 over 2 times root 2 over 2. Okay. I know this looks bad, but it actually gets a lot better, a lot faster from here. Our numerator is going to go to root 6 minus root 2 over 4. Our denominator is going to go to negative root 2 minus root 6 over 4. And when we think about what we're doing here, we could rewrite it like keep the first fraction times flip the second fraction. And check this out, these 4's actually reduce. And so we'll end up with root 6 minus root 2 over negative root 2 minus root 6. And if you type this number into the calculator and you type this number into the calculator, they should be the same value. Okay. So pick your poison with tangent. I think the formulas are definitely a little bit more complicated. I think they're complicated in different ways, so it's really your choice which one you want to use. All right. Let me pause here for a moment and see if there are any questions. Can you and should you reduce the answers? I don't need you to reduce them. I think there's plenty of work already here. You can totally leave them the way they are. Yeah. Okay. Cool. Thanks for asking. Yeah. I mean, some things it's like you don't need to reduce it, right? There's so much work that's gone into it already. All right, cool. So it sounds like some folks are like, yeah, I'm going to stick to the first one. That is totally fine. Anyone in here feeling like the second one is more right up their alley? Okay. Yeah. So I think you're going to find that different things work for different folks, right? And that's totally fine. Both of these formulas are valid. So let's do this. Let's take a look at example 12. And all I want us to do is figure out first which two angles. Before I continue, Gloria brings up a great point, which is maybe we use both the methods and you could kind of use it to double check your answers. That's not a bad strategy. Okay. But let's think right here for tangent in example 12. we need to come up with two fractions that when we add them or we subtract them is going to give me 1 pi over 12. Okay. So I'll give you a moment to kind of think about what numbers might give you 1 pi over 12. And this is a little different from some of the other ones we've seen. Two minus one, yeah, we could do like a 2 pi over 12 minus 1 pi over 12, right? That would give us 1 pi over 12, right? And this one reduces to pi over 6, which is great, but this one doesn't reduce, okay? So let's try out the other suggestion. Maybe we try 9 and 8 or 3 and 2. Okay. Let's try both of those. Okay. So those were both suggestions from the chat. And let's see. This first fraction, let's make sure I do this right. 3 pi over 12 is the same as pi over 4. That's good. 2 pi over 12 is the same as pi over 6. Okay, that's also good. All right, so it looks like Thea's second suggestion of 3 minus 2 totally works here. Now let's check out the other suggestion. 9 pi over 12 reduces to 3 pi over 4. Well, that's good. That's on our unit circle. And 8 pi over 12 reduces to 2 pi over 3, which is also on your unit circle. Okay, so I would say that you could work with either one of these. All right, either one of these pairs would work. All right. So let's do this. I'd like us to take a look at example 12 and example 13. All right. And I'm going to put you into some breakout rooms to kind of play around with this because I think there are probably questions that maybe folks don't really want to ask me out loud in class or whatever it might be. But there's probably also folks in here who might have different explanations for like how we get these numbers that might be more understandable to you. Okay. So let's go into some breakout rooms. Let's go for maybe about 15 minutes and let's take a look at 12 and 13. If you and your group finish early, then you can certainly go on to 14 and 15 as well. All right, so those are identities just to kind of play around and see, like, based off of what we've learned, what are some new strategies and formulas that we can use in identities, okay? So let's go into some breakout rooms for about 15 minutes, all right? And at the least, we want to finish 12 and 13. All right, folks, let's wait for everybody else to reappear. And then I'd love to hear what you all accomplished during this time, how you use the formulas, which formulas you chose to use. All right. Looks like everybody made it back. I hope that was a helpful session. Is there anyone who would like to share what their group did for example number 12? Which one did you use? Which setup did you use? Which formula did you use? What solution did you get? You find all the tangents. Okay, cool. And I'm assuming your group used the 3 pi over 4 and the 2 pi over 3, yeah? Okay, all right, cool. So let's set that up and let's see what we get. So if we have tangent of 3 pi over 4 minus 2 pi over 3, we know that's going to be tangent of 3 pi over 4 minus tangent of 2 pi over 3 over 1 plus the product of those. Okay, cool. All right, and when we plug in our numbers, let's see, tangent of 3 pi over 4 should be -1 minus tangent of 2 pi over 3 should be -√3 over 1 plus -1 times -√3, and that should give us -1 plus √3 and 1 plus √3. Yeah, okay. All right, well, no matter which version you use, and I know it's a lot of radicals and pies and fractions and all of that, but we should have gotten -1 plus √3 or 1 over 1 plus √3. Um, Yeah, and whatever you get, if you use the other formula, if you type in that decimal, it should give you the same decimal as you get over here. Okay? All right. Any questions come up for example 12 as you work through that one? All right. Well, if you have questions later on, let me know. All right. So for example 13, how did folks approach example 13? How did you verify that identity? Or what ideas did we come up with? Okay. There's one I got stuck. I mean, I would look at the formulas from today, right? Like that's the theme of this section. 6 formulas to look at. Do any of them look like we could use them for either side here?
I use the first set of formulas that is like pasted into our notes.
Okay. So what did you get for did you replace the left-hand side?
Yeah,
And so when you replace the left-hand side, what'd you get?
I got tangent of x plus tangent of pi over 4 divided by 1 minus tangent of x times tangent of pi over 4.
Perfect. Okay. So, yeah, I mean, I think it is really easy to kind of get lost in all these formulas, all right? Which is why we're trying to kind of practice identities as we go. But when we look at this one, this is our tangent sum formula. Now, why would we pick the one that has all the tangents and not the one with the sines and cosines? Right? Because we sort of have two versions we could pick. We could do the one that Isis just said, or we could do the one where it's like sine theta, cosine theta, blah, 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 over all the other stuff. Like, why would we pick the tangent one here? Yeah, exactly. Like, we could turn everything into sine and cosine, but what are we trying to achieve? We want something that has tangents in it. So if we want something that has tangents, we should probably stick with things that have tangents in them, even if one of our go-to tricks has been to convert everything to sine and cosine. right? That trick, maybe it's something that you feel confident with, but might not be super helpful in this particular scenario, okay? All right, so we have some things that have variables. So like tangent x we can't really fix, but what can we replace tangent of pi over 4 with? Yeah, this we can replace with 1, and that means we could replace this one with 1 as well. And so let's see what happens when we replace it with 1. We get tangent x plus 1 over 1 minus tangent x. All right. Now when we add numbers together, tangent x plus 1, that's the same as 1 plus tangent. So we do have our identity here where both sides are equal. Okay. All right. So I know sometimes it's a little scary when you have here, but turns out that this one actually wasn't too bad once we found the right identity to work with. Okay. All right. Well, folks, we've got 2 last questions to take a look at. Okay, 2 last questions. So example 14 and example 15. All right. So with these ones, what we're looking at here is we want to think, all right, we've learned so many identities at this point. What might be useful? What might not be useful? Okay. So what I'd like to do right now is not solve 14, but I'd like to uh, have you folks brainstorm some ideas. All right. So what are some of the formulas that we might want to use based off of the lesson from today and the way this identity is set up so far? What might be some good identities to use or formulas to use from earlier today? Sum and difference formula for sine. Okay, so this one, it looks like it could be the sine sum. And we could, as Thea said earlier, we could expand it, okay? And this one over here, maybe the sine difference, okay? All right. Does anybody else have ideas on what we could use for example 14? Because sometimes there's more than one option and sometimes there's one like pretty clear option, okay? Anything else kind of jumping out at folks in terms of ideas on what to use for 14? Okay, yeah, sum and difference. Okay, so let's leave that one for a moment and let's take a look at number 15. Okay, so let's take a moment, look at 15 and what identities or formulas are kind of jumping out at us right now. What identity is that? What identity would we say that was? A co-function identity? That is not a co-function identity. What other ideas do we see, or what other identities might we want to use for this one, or try? Because really that's all we can do is try. Ethan's all yelling at everyone. Um, can we convert it to sine and cosine? Yeah, you could maybe try converting things to sine and cosine. Convert to sine and cosine. Okay. All right, let's see if we could come up with maybe one more idea. What's one more idea we have here? It doesn't even have to be an idea. It could be like, oh, I think we could use this formula from it that we learned earlier. Okay, can you be specific, like which sum and difference, sine, cosine, or tangent? Because we've got all of them in here. Okay, so sum and difference for tangent. Well, you could use sum and difference for tangent if you had this. But this is not the same as that. Okay. Yeah. All right, but let's see. Ethan says work on the left-hand side with the sign on the top. So maybe here we could do the sign difference identity. Yeah, that's definitely a possibility. Okay. All right. So I think that part of the I think that one of the important parts of working through these, yes, it's helpful to walk through, have someone walk you through the answer, but I think it's equally important, if not more important, to put your own ideas out there. Okay, which is why I asked us to kind of think about what ideas we might have here. If that's something that you feel comfortable doing right now, that's a great place to be. If you feel overwhelmed, you don't know the identities, then I would make sure that you grab a sheet of paper, write down all your identities so you have them there. Okay. But we don't want that to be a situation where we're just like, I don't even know. Okay, we want to have at least a couple ideas, at least one idea about like, okay, this looks like this formula. Let me try this. Okay. And so what we're going to do today is I'm going to put you all back into breakout rooms, all right? But we are not going to come back together as a class. But your classwork for today is to work through example 14 and 15. And I'm going to create an assignment on Canvas. So once you're done with 14 and 15, just upload a PDF that has your work for that, and that will be your classwork for today, okay? So we are not coming back together as a class. Once you and your group are done with the identities, then you can go ahead and turn those in individually, and I will probably close the rooms at 12:35 or whenever class is over, okay? So are there any clarifying questions before we go into our breakout room?